Hello everyone, welcome back to Chemical Engineering and Aspen Channel. As you know, these days we are focusing on the module of Chemical Reaction Engineering, and so far we have published 35 videos related to it. So we are today bringing the lecture number 36 for our valuable viewers, in which we will be focusing again on chapter number 7, and as a recap of the integral method which we have studied in our lecture number 35, that for zero order, for first order and for second order system, we have to draw a plot between time and C of A for zero order system. If it's a linear plot, then the zero order system is confirmed. If it is not a linear plot, then we will move to the first order and we will draw a plot between time and natural log of Ca naught over Ca. If it is a linear plot, then we have guessed the correct reaction order. If it is still not, then we move to the second order system and we will plot between time and 1 over Ca. And accordingly, if it is a linear plot, then we say that the reaction order is second. However, if none of these plot is linear, it means that we cannot use the integral method and we have to go for some other methods like the regression analysis or some other techniques. So using this concept, we will now be solving an example related to it, and that example is example number 7.1, which states that the liquid phase reaction trityl, which is represented by A, and methanol, which is represented by B, these two react to produce a product which is C. This reaction was carried out in a batch reactor at 25 degrees centigrade in a solution of benzene and pyridine in excess of methanol, which is Cb naught is equal to 0.5 mole per cubic decimeter. So it has been said that one of the reactant, which is methanol, is in excess quantity. And if you remember our previous lectures where we had said that one solvent is in excess, so we had said it is as a pseudo first order system. If you remember our example number 5.1, I'm giving it in the pop-up. Pyridine reacts with HCl, which then precipitates as pyridine hydrochloride, thereby making the reaction irreversible. So the reaction is irreversible. One of the reactant is in excess. The reaction is first order in methanol. The concentration of triphenyl methyl chloride, which is A, was measured as a function of time and is shown below. That for different time intervals, the concentration is given to us, and you can see the concentration of A is obviously decreasing because it is a reactant. Reactant is consuming, and obviously the product is producing. We have to use the integral method to confirm that the reaction is second order with regard to our species A, which is triphenyl methyl chloride. We have to obviously build the equations. We have to then come to the second order system, and then we have to say, or we have to prove using integral method that it is a second order system. And for this, we have to draw a plot between time and 1 over Ca. So going to the solution, if we assume that this model is following the power law and we say that beta is 1, as it has been said that the reaction is first order in methanol. So accordingly, this equation will become minus Ra is equal to Kca raised to power alpha Cb raised to power beta, but beta is 1. So obviously Cb raised to power 1. Now we have been said that methanol is in excess, which means that Cb naught is approximately equal to Cb. So accordingly, we combine that K and Cb naught, like you can see here that we have replaced Cb by Cb naught, and then we combine this Cb naught and K to produce that K prime, which is our pseudo reaction rate constant. If you remember that we had done these calculations in our chapter 5 as well. So it is K prime Ca raised to power alpha. Now what we will do, we will first find the value of this K prime, and then we will find the value of this K actually, where K prime is the pseudo rate constant. K prime is equal to Kcb naught, while K is the true rate constant. So these are two different terms. Now we put alpha is equal to 2 because in the statement it has been given to us that use the integral method to confirm that the reaction is second order with regard to the species A. So accordingly, we put alpha is equal to 2. Accordingly, this equation will become minus R is equal to K prime C raised to power 2. And we know minus R is equal to minus dC over dt, as we have derived multiple times in our previous lecture. So minus R is equal to minus dC over dt, and that is equal to K prime Ca square. If we integrate it, this equation, we get T is equal to 1 over K prime, 1 over Ca minus 1 over Ca naught. K prime is multiplied with this T. Accordingly, we get K prime T. 1 over Ca is left here, while 1 over Ca naught is taken here. So 1 over Ca is equal to 1 over Ca naught plus k prime into t, and that equation corresponds to y is equal to mx plus c, where y is 1 over ca, m is k prime, x is t, while c, the intercept, is 1 over ca naught. So now what we will do, we will generate a plot between time and 1 over ca, as I have shown you in the start of the lecture as well, that for second order system, draw a plot between time and 1 over ca, and accordingly, once we draw this plot, if it is a linear plot, then the reaction order is confirmed. So if we get the linear plot, we are proving that this is a second order system. And you can see here, we will in a couple of minutes go to the Excel sheet to confirm this. The time at x-axis 1 over ca, at y-axis, according to the linear plot, is generated at the slope of this line is k prime, which is 0.12 cubic decimeter per mole per minute. So now quickly going to Excel sheet and now solving it. So now coming to the Excel sheet, we can see that given the data of time versus concentration, and for second order system, we have to draw the plot between time and 1 over ca. So first we will write 1 over ca, the unit will be cubic decimeter per mole, and according to that is equal to 1 divided by this, which is ca, and we will simply drag it. Then what we will do, we will simply draw a plot, time, control button from keyboard, then selecting the second row, insert, and then drawing the plot. And now you can see that the plot is generated over here. And now we have to simply find the trend line. So right click on it, add trend line. This is obviously a linear line going to display equation on chart, and you get 0.1236. So the slope is approximately 0.12, and that slope was actually the k prime. So that is 0.12. So the value of the k prime is 0.12, as we have seen in our slide as well. We have seen that we get the value of k prime as 0.12. So what we need to do, we know the value of k prime, which was actually kcb naught, or we can say k is equal to k prime over cb naught. Now the value of k prime is 0.12, while that of cb naught is 0.5. So once we divide these two, we get 0.24 cubic decimeter per mole whole square divided by minute. This is the actual answer of K, which is the true reaction rate constant. Well, for the pseudo, we have to generate it because we have to solve the system. So now the rate law will become as minus RA is equal to K CA square CB. This is the actual system. If you remember, we had solved in example 5.1 or 5.2 the pseudo system. We can apply the same concept over there, that once we had find out the value of K prime, we can simply substitute it by, and we can get the value of K over there as well. This is one way of doing it. But now we have seen in data analysis that firstly we make the system pseudo first order, then we find the value of that pseudo rate constant, and then we come back to the true rate constant, and then we write the complete equation, which is minus RA is equal to K, which is 0.24 CA square, because we have proved that it is second order with respect to A, and we were given that it is first order with respect to methanol. So actually it is a third order reaction system. Like if we count the total order 2 plus 1, so accordingly it's a overall order is third in the system. So if we go to the analysis, in this example, the reaction orders are known. So the integral method can be used to verify the reaction order, and accordingly to find the specific pseudo rate constant, which is K prime is equal to KCB naught for excess of methanol. Knowing K prime and CB naught, we can then find the true rate constant, which is K. So I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box, and I would be happy to answer it. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video, and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.